Today, we're going to dive into a mathematical method that completely changes the game for solving some seriously complex equations. It's a theorem that tackles problems mathematicians literally thought were impossible to solve. So yeah, let's just jump right in. So, let me ask you this. Are some math problems actually impossible? I mean, for centuries, the consensus was, yeah, absolutely. For certain kinds of equations, finding a perfect, exact answer just wasn't in the cards. But what if that entire assumption was wrong? For hundreds and hundreds of years, one of the biggest mountains to climb in math has been solving these high-degree polynomial equations. Finding their roots, the specific values of x that make the whole thing equal 0, gets unbelievably tricky as the equations get more and more complex. Okay, so this is the absolute key difference we need to get our heads around. An approximate answer versus an exact one. See, computers can get you a close enough decimal, but there are always tiny rounding errors. An exact answer, what we call a symbolic answer, is perfect. It's infinitely precise. And for these problems, that's the real holy grail.
And this wasn't just a hunch. This belief was actually formalized. There are famous ideas like Abel's impossibility theorem, which basically proved that you can't solve certain polynomials using the standard tools. Addition, subtraction, square roots, that kind of stuff. It really seemed like math had hit a hard wall.
But this is where the story gets really interesting. Ezouidi's theorem enters the picture, and it basically just challenges everything we thought we knew. It lays out a brand new, structured way to find those exact roots, completely bypassing the old roadblocks. Now, the formula at the heart of this theorem, look, it's a beast. Seriously, it's a giant wall of symbols. So instead of just throwing that at you, let's focus on the idea of how it works. The secret sauce is that it's a recursive process. It builds the solution one step at a time, which means it never has to guess or approximate. So you can think of this whole thing less like a formula and more like a recipe. First, it takes binomial coefficients. Think of them as mathematical Legos. It mixes those with the numbers from our original equation, and then, and this is the most important part, it uses that recursive process. Each step builds on the one before it to systematically hunt down those perfect, exact values. All right, enough theory. Talk is cheap, right? Let's see this thing in action. And we're not going to start with some simple, easy example. Oh no, we are going to throw a true monster at it, a massive 14th degree polynomial, and really see what this theorem is made of. And there it is. Just look at that thing. It's got 15 different terms. Trying to wrestle with this using the old methods would be a total nightmare of approximations. But with Ezouidi's theorem, we've got a plan. We can approach it step by step. So let's get into it and see how this thing works. The theorem lets us calculate a whole new set of coefficients, which we'll call a sub r. And these little guys are the keys that are going to unlock the entire solution. We start running the numbers through the recursive process, and right away, something pretty weird happens. The very first coefficient we calculate, psi 0r, just simplifies down to 0. And then a really powerful pattern starts to take shape. As we calculate the next ones, they also just become 0. S1r, S2r, all the way through S5r, they all just collapse to nothing. It's like the method is actively filtering out all the mathematical noise. And then, bam, we hit something. The sixth coefficient, S6r, is not 0. It's this precise, beautiful, symbolic value. This is it. This is the first critical piece of our puzzle. And just as suddenly as it appeared, the pattern of zeros comes right back. S7r, S8r, all the way up to S12r, all 0. The process is just methodically weeding out everything that doesn't matter for the final answer. And then we find it. The second and final crucial piece of the puzzle. The 13th coefficient gives us another non-zero value. And with that, we're done. We now have everything we need to crack this thing wide open. And this right here is where the magic happens. Remember that 15-term beast we started with? Because almost all of our new z's coefficients vanished into 0, that entire monster equation collapses into this beautifully simple 3-term equation. And this is something we can actually solve. And when you solve that much simpler equation, you get this. Now, I know it looks incredibly complicated, but the amazing part is that every single piece of that answer is built directly from those two non-zero values we found. It's not a guess, it's not an approximation, it is the perfect, infinitely precise answer. I mean, just look at the difference. On the left is what you get with older methods, a decimal that's just close enough. On the right, you have the exact symbolic truth. The difference isn't just big,
It's fundamental.
And that really is the heart of it all. This isn't just another calculator trick. It's a profound shift that gives us, quote, precise solvable roots for polynomials that would otherwise be deemed unsolvable. It's a complete game changer.
So, okay, this is obviously really cool if you're a mathematician, but why does this matter to the rest of us? Well, it turns out that this level of precision has huge, and I mean huge, implications for the real world.
Just think about fields like physics, engineering, and computer science. If you're designing a jet engine, or modeling a complex financial system, or calculating the trajectory of a spacecraft, close enough can be catastrophic. You need exact answers to make sure things are safe, stable, and accurate.
And that's really the big takeaway here. Ezouidi's theorem hands us a universal key. It's a massive leap forward that gives us a clear path to find the perfect, symbolic roots for any polynomial, no matter how ridiculously big or complicated it is. And it just leaves you with this incredible thought, right? For centuries, this type of problem was considered a dead end, a hard limit to what was possible in math. Now that limit has been shattered. So you have to ask yourself, what other problems that we think are impossible today are just waiting for the next breakthrough to come along and prove us wrong?
So this is, as you see, 14-degree form equation has been solved by the Sultan Ezouidi, and we brought the exact samples. Okay, hope I got benefit from this lecture, and see you next time.